In industry, it is impractical and costly to obtain all available data about a process. A sample from the population proves to be of equal value and usefulness in describing and inferring behavior. Of course, how we collect this sample matters greatly and drives the effectiveness of the data. True random sampling requires giving every element an equal chance of being selected for the sample. This can be exceedingly difficult. Humans have subconscious biases that prevent us from truly selecting randomly. We need tools to help. Random samples must be representative of the population and not just a grouping of parts readily available. Selection requires careful planning and organization. Very often, we use random number tables to assist us. In manufacturing settings, this can be troublesome due to a lack of time and understanding. For this reason, true random sampling is very difficult to realize in many real-world applications, especially where technology is lacking. Sequential sampling plans are similar to multiple sampling plans, except that they continue indefinitely. These plans are stopped after a designated number of rejects have been uncovered out of a number of samples assessed. They are based on the following factors: producer's risk or alpha, consumer's risk or beta, acceptable quality level, and rejectable quality level. In the plan above, there are 3 regions: green, accept the lot; red, reject the lot; yellow, check more. The size of these regions are dependent upon the inputs mentioned above. For each class of product produced, inspect samples as long as the sample size and number of defectives lies in the yellow zone. If the number of samples checked compared to the number of defectives found falls in the green zone, accept the lot. If the number of samples checked compared to the number of defectives found falls in the red zone, reject the lot. An advantage to this approach is a substantial reduction in the number of samples required. This is on average a 50% reduction when compared to equivalent single sampling plans. A disadvantage is that there is no upper limit on the number of samples that might have to be inspected or needed to make a decision to accept or reject the lot. This can be overcome by truncating the sample to an agreed upon value and devising an appropriate inspection termination point, an action plan if ever reached. In random sampling, it is assumed that the sample is randomly selected from a homogeneous lot. Lots may not be homogeneous. Parts may have been produced on different lines, by different machines, or under different conditions. Equipment can be maintained across lines differently or be of different ages. Stratified sampling is the selection of random samples from each subgroup or strata of the lot. The resulting mix of samples drawn can be biased if the proportion of the samples does not agree with the relative frequency of the subgroups. Stratified sampling is not as robust as random sampling, but it is considered one of the better choices. Systematic sampling has a lot of uses in real-world processes. It is very easy to implement and maintain. Essentially, a sample is taken at some regular interval based on time or frequency. It is advisable to vary the interval to ensure a more unbiased sample. This can create complexities. Systematic sampling is somewhat biased. Despite pre-planned efforts to vary intervals, there are still gaps in which excessive process changes can occur and result in huge swings in production performance. Cluster sampling involves the dividing of the lot into subgroups. Subgroups are randomly selected and every element in the subgroup is assessed. This method is considered biased because subgroups can be overlooked. If there is a correlation between the subgroup and the time of production, process, influence factors, or location, then swings in the process can go undetected. Such methods are used when we wish to understand the opinions of a localized area of a state or country. Geographic segmentation is a common type of cluster sampling. Convenience sampling is the most undesirable and biased method from a randomization standpoint. As the name implies, convenience sampling takes place with the participants that are easily accessible. In pilot testing, convenience sampling is very common. This method is considered a non-probability sampling method, since the requirements for inclusion are extremely minimized. Convenience sampling is prone to sampling error due to the high lack of representation. It is very cost-effective and quick to execute. Determining the sample size is dependent upon the estimated behavior or the distribution of the process or situation. In a successive course, we will discuss some common ways to estimate the sample size based on the level of significance, estimated distribution, standard deviation, and the desired level of precision. Attaining enough samples in any analysis is critical with respect to the strength of the inferences we make. Too few samples weakens the conclusiveness. In other words, increases the likelihood we make the wrong decision. The more samples we can collect, the more confidence we can enjoy.